Hey everybody, let's talk thermochemistry. Thermochemistry is chapter 5 in your textbook. I'm going to want you guys to, after this lecture, I obviously want you to be reading the textbook. I want you to be looking at all of those really great diagrams that are much better than my terrible drawings that you're going to see here today in this lecture. I want you guys to take notes, obviously. Pause the video anytime you feel like you need a little bit of extra time. And any questions that you guys have, I will answer when I actually see you in class or on Zoom. All right, here we go. I hate talking into the void, so I apologize if I sound ridiculous. It's late at night. I'm tired. Hopefully this makes sense. Here we go. All right, thermochemistry is the study of the energy associated with chemical reactions. Now, when I say associated, what I really mean is the energy that is absorbed or released by chemical reactions. So maybe I should have written that the first time. So absorbed, I'm already like making things I don't want. Absorbed or released by reactions. And that's really important to us, right? Because we can do stuff with the energy from reactions. You know that, right? We can charge our batteries. We can drive our cars based on combustion or now on electrical potential energy. So the energy of chemical reactions is sort of what makes the world go round. Hello, metabolism, photosynthesis. Here I am just talking about driving cars, but things wouldn't be alive without the energy associated with chemical reactions. So that's what we're going to study here in chapter 5. Now we're going to study this even more in depth in chapter 20 in the studies of thermodynamics, which takes into account some additional factors. So we're going to revisit this again later. But for now, you know about different types of reactions. We just spent chapter 4 talking about reactions taking place in solution. We're obviously going to talk more about other types of reactions like acids and bases and redox reactions later in the year. All of these reactions have energy associated with them. And so that's what we're going to study right now. But we use this term energy all the time. What is it, right? What the heck is energy? Do you even know? Well, energy is the ability to transfer heat and do work. Hopefully my pen scratchy isn't too loud. I bought this fancy microphone and it doesn't sound any better than these dumb headphones I'm using to record. It's kind of annoying. It's probably because I don't know how to set the fancy audio settings on it. I'll figure it out later. Okay, so what the heck do I mean by heat and work? All right, so let's talk about what heat and work are, right? We can't be having these definitions where we don't even know what the words within them mean. So for heat, let's use red. That was an ugly line. Heat in chemistry is quantified by the variable Q. And heat is the ability to change temperature. And when you think about that, changing temperature means temperature can increase or temperature can decrease, obviously. And when you think about heat flow, heat always flows spontaneously. In which direction? Think about it. It goes from, I didn't leave myself enough room to do work in here, that's annoying, from high to low temperature environments. So that's what heat is. Well, what the heck is work? Work. Oh, I think I want to use a different color for work because because I think I want blue feels cold to me. All right, let's use this bright green here for work. Work is quantified by the variable W. And work is the energy used to cause an object to move against a force. Okay, so energy used to cause an object to move. And if you want to be all physicsy about it, you could say against a force. Okay, so think about it. Like, work is taking this brick and pushing it, across the table. It takes work for this brick to move across the table. I guess my arrow would be better over here. Ooh, don't be judging me with those force diagrams here. Okay, let's just go ahead and talk about how we actually measure work. So work in physics is force times distance, right? Like, how far did we push this brick and how much force was applied in order to do that? Now, when we're talking about chemical reactions, we're not talking about like bricks moving across a road or cars moving down a road. How does a brick move across a road, Amanda? Ugh. In chemistry, the type of work that gets done is the expansion and compression of gases. Okay, so like if you have, let's say, a piston here and a reaction taking place inside this piston, and if gases were created by this reaction and these gases expanded, this piston would move up, right? And the volume here would get bigger. This is called pressure volume work. And this is the type of work that we're going to be doing in chemistry. So this is called, I don't want you to think it's underneath this diagram. Now I'm running out of room. I'll scroll. This is called pressure volume work. The expansion and compression of gases. And the way that we actually calculate the magnitude of that type of work is equal to negative P delta V. So this is the equation we really care about here for chemistry. And this one, your physics teachers care more about. Okay, so P stands for pressure. Okay, so we're usually talking about atmospheric pressure. That piston would be moving against the pressure of the atmosphere. And V is obviously your change in volume. Whenever we talk about changes in chemistry, you guys, it's always final minus initial. Okay, so the change in volume is the volume final minus the volume initial. So in the particular example that I just gave you guys, where gases were produced by this reaction and the piston moved up, like there was this expansion, the volume got greater, the final volume minus the initial volume would be a positive value. And so the work would be a negative value. And we're going to talk more about why we want that to be a negative value a little bit later on, or what that negative value for work really means, okay? It's going to have to do with identifying the system versus the surroundings, but we're not quite there yet, which is maybe why I should have waited to talk about these equations. But such is life. Okay, so here we go, back to sort of an overview of our discussion about what energy is. Let's review. Energy is the ability to transfer heat, right, for the temperature of an object to change or to do work. Now, in chemistry, that would be gases expanding or contracting and the volume of the container thus changing. That's what energy is. All right, now there's different types of energy. You guys are familiar with these different types of energy. We're going to be talking a lot of physics here. Ooh, do I remember what the heck color I was using? Does this color match? Yay, I picked the right one. Okay, types of energy. What are the two types of energy, you guys? You know this? Do you do? Kinetic, energy of motion, and potential. That's right, energy of position. Okay, so kinetic energy is the energy of motion, and potential energy is the energy of position. But again, like we were discussing with work, I want you to take sort of your understanding of this in terms of physics and apply it to the particle level. Like, what does this mean for atoms and for molecules? When we're talking about kinetic energy, it's the same equation it was in physics. Kinetic energy is equal to 1/2 mv squared. Same equation. But let's think about what we're talking about here. Like, what's the mass that we're talking about? The mass that we're talking about is the mass of the molecules in the sample. The velocity is how fast are those molecules vibrating, if we're talking about a solid. How fast are they flowing, if we're talking about a liquid? How fast are they flying around the container, if we're talking about a gas? So this is the same equation that we would be talking about. Now remember, kinetic energy is essentially temperature. Or should I say that temperature is a measure of average kinetic energy. In other words, when the molecules are moving fast, you're going to have high temperatures. We're talking about things that are hot. When the molecules are moving more slowly, we're talking about a sample that is more cold. Okay, so how fast are these molecules moving will relate directly to their temperature. And that's what we call kinetic energy. When we're talking about potential energy, back to our physics example, like when you're standing at the top of a mountain, or when the ball is sitting up here at the top of the mountain, it's got a lot of potential energy and it's going to roll down the hill. This is the energy of position. Lots of potential energy. Down here at the bottom of the hill, less potential energy. But what does that mean in terms of molecules, right? We're not talking about molecules sitting on the top of a hill. In chemistry, when we talk about potential energy, we are talking about electrostatic potential energy. I am not leaving myself enough room. We talk about electrostatic potential energy. This is all about the attraction or repulsion of charged particles. Okay, so attraction or repulsion of charged particles. And here is your equation for electrostatic potential energy. K is a constant. Q1 is one of your charges, the magnitude of one of your charges. Q2 is the magnitude of one of your other charges. And D is your distance between your charges. Okay, so Q represents your charges, and D would be your distance between the charges. So where is this really going to come into play for us here? It's going to come into play when we start talking about the attraction of positive and negative charges to each other in ionic compounds. It's going to come into play when we talk about strengths of intermolecular forces. Okay, so if we're talking about charges, like a positive and a negative, these charges attract one another. And the closer these two charges are to one another, the stronger their electrostatic potential energy, right? Because if you have a small distance between those two charges, the stronger or the greater that electrostatic potential energy is going to be. Okay, so this is going to govern lattice energy of ionic compounds and strengths of intermolecular forces. All right, now, we don't even need to actually like do any calculations here. We're really just going to talk about this equation qualitatively. All right, so those are our two different types of energy, kinetic and potential. And remember, energy is the ability to transfer heat or to do work. How do we measure it, right? Like, what are these units that we use to actually measure energy? And you guys are probably familiar, like, with these units, again, from physics or from just, like, eating a candy bar. The word calorie sound familiar? Yes, Ms. Rivera, it sure does. But let's get there. Let's not get ahead of ourselves. Let's not get to calories just yet. Let's think about like where these units of energy actually come from. Let's like derive the unit of energy. So if we look at the kinetic energy equation, 1/2 mv squared, if we measure mass in our SI base unit, which is kilograms, and velocity in meters per second, and then we square it, the unit that we end up with is kilogram meter squared per second squared. And that's kind of like a big mouthful of a unit. We call this unit a joule, 1J, a joule. And the joule is the SI base unit for energy. So perhaps we could put that in a little equation box. There you go. And of course, we're going to be using kilojoules a lot as well, right? So 1 kilojoule is equal to 1,000 joules. Don't forget your unit prefix conversions. Now, how does this come into play with a calorie, right? So calories are the unit that you'll see on the back of your candy bars, and we will use a lot when we are doing calorimetry, which is a laboratory technique used to measure heat transfer and energy of reactions. Okay, so 1 calorie is equal to 4.184 joules. Okay, this is a conversion factor that you should just know. And just like for, your everyday sort of understanding of energy and what you're reading on the back of your nutritional things, a dietary calorie like when you see, like the candy bar is like 250 calories, a dietary calorie is actually equal to 1,000 calories. We call dietary calories in chemistry 1 big C calorie, which is equal to those 1,000 regular calories. Like a dietary calorie is really 1 kilo calorie. So really, that would look a lot worse on the back of your candy bar, right? 250,000 calories. Okay, but that's not super important. That's just like interesting little side note or factoid. But you do need to know that 1 regular calorie is 4.184 joules. It's very important for us to be able to transfer between calories and the SI base unit of joules. Okay, moving right along. Let's talk about system versus surroundings. Whenever I'm talking about system versus surroundings, the system is the thing we're studying, the thing being studied. It's really fancy, isn't it? Really fancy definition. Studied. In our case, for chemistry, the thing being studied is always the reaction, right? What's going on with the molecules? The surroundings, I did not leave myself space to draw a nice little arrow for surroundings. It's gonna have to like go through. Oh, let's do this. Ooh. Oh, that looks gross. You guys, it takes everything in me to not like start this whole recording over. I like annoy myself from talking too much and drawing annoying things like that. But we can't be perfectionists or we're all gonna be up way too late. Okay, the surroundings is everything else. Oh my gosh, if I'm annoying myself, I must really be annoying you. Sorry. All right, the surroundings is everything else outside of the reaction. Now, this is going to be important to be able to differentiate between these two things, because in the lab, we're often only able to measure the surroundings. We can't get in between the molecules and measure the system itself, okay? We have to really measure the effect of the system or the reaction on the surroundings, because you can't get that thermometer. Imagine like taking that thermometer and trying to like stick it in between two particles to measure, heat flow or temperature change. We're not able to do it, but we are able to measure the temperature change of like the solution that the reaction is happening in, okay? So that's why it's going to be important to identify what is the system and what is the surroundings. Now, we also further define systems, systems only. Okay, so these things here, these words down below apply to systems. Maybe I should say like types of systems. Types of systems. An open system, you guys, is something that allows both matter and heat to be transferred. So like think about it like if you have just a pot of boiling water. It's my boiling water. I'm such a good drawer. Here, I'll put some fire under the water. Fire. So a pot of boiling water can transfer heat, right? From the pot out to the environment. You put your hand up above that pot, it feels very hot. And matter can leave that system as well. That's why we call it an open system. You can transfer heat and matter. Okay? A closed system would be like if you had a lid on that pot, a tightly sealed lid. Now, of course, pressure would go up. You wouldn't want to explode the pot or anything. Where, we can still, that lid is going to feel hot. The sides of the container are going to feel hot, right? So it's not insulated. It's just closed, okay? So when the system is closed, you can transfer heat, but not matter. Ooh, my handwriting's starting to get, you can tell, starting to rush. Heat, but not matter. And an isolated system would be like a thermos, where you have like an insulated situation where your water stays hot. Okay, so this would be like insulated. And no heat or matter transfer. Got it? Oh, I didn't draw the fire under my other pot. And this is hot water in here. And it's going to stay hot because it's isolated. All right. Moving right along to section 5.2. The first law of thermodynamics. Oh my gosh, you guys, this is so important. First law, energy is conserved. Boom. How easy is that? Now, when we're talking about energy, we can also call it the internal energy of the system. This is really what we're talking about here. The variable for energy is E. So we've talked about units of energy. We've talked about types of energy. We've talked about what the heck energy even is, okay? So the internal energy of the system is always conserved. And that's what the first law of thermodynamics tells us. And so you can also define internal energy as the sum of all kinetic and potential energies of a system. That's what internal energy is. We've got a couple of equations that we can use here for internal energy and change in energy of a system. The first equation is that the change in energy of a system is equal to heat plus work. Right? Because energy is the ability to transfer heat or to do work. And so that's how we can actually calculate the change in internal energy, is to look at how much heat was transferred and how much work was done. Another way to calculate the change in energy of a system is if you just straight up know how much energy something has in its final state minus how much energy it has in its initial state. Right? So if something has more energy in its final state than it has in its initial state, you would end up with a positive change in energy, like that system gained energy. So if you got a positive delta E, the system gained energy. And if you have a negative delta E, in other words, you started off with a bigger value, you had more energy at the beginning than you had at the end, that would result in a negative E, and that means that the system lost energy. Just really check and make sure my thing is still recording my voice. Yep, everything looks good. Okay, now these energy, the amount of energy something has at the beginning and at the end can be diagrammed with something called, just an energy diagram. And so if we have energy increasing here on our y-axis, this is total amount of energy, and let's say the initial amount of energy we had was here, so this is our energy initial, and here this line represents our energy final. You can see here we would end up with a positive delta E, where we went from having less energy to having more energy. And of course, the opposite could also be true, where we have an energy diagram that looks like this, where we've got increasing energy on my y-axis. And if my initial energy state is up here with a higher amount of energy, and my final energy state is down here with less energy, right? Like if this is 0, down here at the bottom, 0. This would result in a negative delta E, where we lost energy. And so these are just called energy diagrams, giving us a sort of visual representation of what happened to the system or in the reaction. Okay, now, when you have something that, like internal energy, where it doesn't matter how the system got there, like it doesn't matter if all of this energy was transferred as heat or if all of the energy was transferred as work, all that matters is your initial and your final states. Variables like that are called state functions. State function is a variable that only depends on final and initial states. In other words, a state function is independent of pathway. So like I said, it doesn't matter how this energy was transferred, if it was transferred as heat or as work or as a combination of both. All that matters is how much energy you have at the beginning and how much energy you have at the end. That's a state function. If you want like an analogy for that, think about like distance traveled. So if I'm like driving my car from Boston to Denver, I could take the shortest route possible. Like I could just drive straight, west, southwest, probably a little bit. I should look at a map. So I could drive, directly to Denver, or I could drive down to Florida and then across to Texas and then north to Denver. And that distance traveled is very, very different. Okay, so the distance would not be a state function, right? Because the distance from Boston to Denver is what it is, but the path that I take to get there could be very, very different. So distance would not be a state function. What would be a state function would be altitude difference, right? So Boston is at sea level and Denver is like a mile high. That doesn't change no matter how I decide to get from Boston to Denver. I'm still going to have that mile high altitude change. Okay, so altitude would be a state function. Driving distance would not be a state function. Okay, enough about state functions. Let's talk about signs. I don't think I made a separate section for this. I did not, but let's just draw. I'm going to leave a little space here to do a little practice problem. And let's talk about signs of heat and work down here. Signs of heat and work. And by signs, you guys, I mean positives and negatives. Like how do we talk about the direction of heat transfer and work being done? So I'm talking about positives versus negatives. Direction of heat flow and work done. Okay, so let's say I have a box, and inside the box is my reaction or my system, right? So inside the box is the system, and outside the box is the surroundings. If the system gives off heat to the surroundings, we assign a sign of negative Q. Okay, so a negative Q is heat released by the system. Okay, or the reaction. When heat is released by the reaction, we say that that reaction has a negative Q value. We also call reactions that release heat like that exothermic reactions. Exothermic, heat being released. And these actually, because we are the surroundings, these feel hot because the heat is leaving the reaction and coming into our hands. And so exothermic reactions feel hot to the surroundings. Okay? If heat is going into the system or being absorbed by the system, we give that a positive Q. Heat is absorbed by the system. And we call reactions like that endothermic. And because we are the surroundings, our hand is the surroundings, our hand are the things providing the heat that goes into the system. If our hand is losing heat, it's going to feel cold. So endothermic reactions feel cold to the surroundings because we're losing the heat. Because remember, heat would flow spontaneously from the hot thing to the cold thing. Okay? All right, so that's how we assign positive and negative signs to heat transfer. How do we assign signs to work? Well, remember, work in chemical reactions is what we call pressure volume work. Okay, so it's easiest to think about this with a piston, right? A piston or a syringe, like something that can change volume against the pressure of the atmosphere. All right, so if this is my system or my reaction, if my reaction produces gas, like, so this is my, my squiggly lines always mean like the reaction is, oh, here I am using hand and arm signals and you guys can't see me. This is my way of showing that the reaction is producing gases. Okay, so if it produces more moles of gas, in other words, the products have more moles of gas than the reactants. If it's producing more moles of gas, what's going to happen to this piston? This piston is going to move up, right? You're going to get an increase in volume. We assign a negative, oh, I was using green for work, wasn't I? And I just wrote all of that stuff in blue. Sorry, I won't torture you rewriting it. Negative W, okay? So a negative W indicates work done by the system. The system is doing the work. Who is it doing the work on? The surroundings. So done by the system on the surroundings. And of course, we could have the opposite thing happen. Draw another diagram here. If we have this piston system again, the reaction's taking place inside here. I don't know why I drew that one so much bigger than the other one. If this system or the reaction produces fewer moles of gas, like maybe the reaction starts off in the gas phase and produces a solid, right? You're going to get a decrease in volume because it would be the gases that are keeping that piston, you know, where it is. So here, this volume would drop down if we had fewer moles of gas inside of here. And so the sign that we assign for that is a positive W. This is work done by the surroundings on the system. And of course, you guys, both of these things can be happening at the same time, right? Like we can have heat transfer happening and work being done at the same time in the same reaction. We're almost done. Let's do a practice problem with this. I think I left myself a little bit of room up here to do that. Not a ton of room, but a little bit of room. All right, here we go. I'm gonna look up a problem so I don't make up anything ridiculous. All right, let's say, so this is a practice problem. And I'm going to take it right from the text. So when you go and read the textbook later, that's right. Yes, Ms. Rivera, we're going to go read the textbook later. This problem will look familiar. Let's say we have a reaction where substance A, which is a gas, is reacting with substance B, which is a gas, to produce substance C, which is a solid. Okay, so if I were thinking about what would be happening if we were inside of a piston here, right, you guys? if this reaction was going from the gas phase, boom, to precipitating out a solid, what's going to happen to this piston as these gases turn into a solid? This piston is going to go down. All right. Now, let's see. This piston going down, let's say that represents, and remember this is going to be a positive sign, 480 joules of work. 80 joules of work are being done by the surroundings onto the system. And let's also say that the system loses 1,150 joules of heat. So remember, if it loses heat, the heat's going this way. And that's going to be a negative sign if it's releasing heat. 1,150 joules of heat. Okay, so remember, your heat is Q and your work is W. What would the internal energy change of this system be? Like if we've got work being done and heat being lost, so here it's gaining a form of energy and here it's losing a form of energy. Well, what is that total energy change going to be? Well, it's just a combination of heat and work, and you just got to make sure that your signs are correct. Okay, so our Q is negative 1,150 joules, plus our work, which is a positive 480 joules. And while this is math that I should just easily be able to do in my head, just don't have any capacity left for anything. Ow, I just have my funny bone on the piano that's sitting right behind my desk. Negative 670 joules. So here's my question, you guys. Did this system or this reaction result in a gain in energy or a loss in energy? And that's easy. The signs for energy are easy, right? Negative means a loss of energy. It released energy, essentially. It ended up in a lower energy state than it started in. Look like this energy diagram right up there. All right. One last thing to talk about. And let me check my notes to make sure I talked about everything. I want to talk about state functions, signs of heat and work, blah, blah, blah. Okay, so lastly, you guys, we're going to talk about section 5.3. Now, don't bother reading section 5.3. It goes way more in depth than you guys need to be worried about right now, okay? Oh man, I really kind of went into my space provided here. All right, so you don't need to read section 5.3 because we're going to just really simplify it for right now. All you need to know about enthalpy for right now is essentially enthalpy is the heat of a reaction. Okay? And the variable that we use for enthalpy is H. So what you're probably wondering is like, why do we need another variable when we just spent all this time talking about heat being Q, right? If these two things are the same. Well, technically they are not the same, okay? Q, heat, and enthalpy are not always the same thing. They are the same thing when the reaction is happening at constant pressure, okay? So enthalpy is equal to the heat of a reaction taking place under constant pressure conditions. Or another way to think about this is when the only work taking place is pressure volume work, which, you guys, for our purposes at this level of chemistry is always going to be the case. Okay, so H is equal to Q as long as you're at constant pressure, which we are always going to be. But the reason why I'm telling you that they are not technically the same thing is because when you guys go on to take like 2 years of thermodynamics in your engineering major in college, you're going to realize that there are times where these two things are not the same, that the heat transfer and the enthalpy are not in fact equal when the pressure changes. So, just note it as a disclaimer, but for now, enthalpy is the heat of a reaction. That's all you really need to know. Okay? So we are going to be looking at, in our next lecture, how we actually measure heats of reaction. But I'm just going to kind of like preview it for you guys right now. And what we're going to be measuring and looking at is, like, let's say we were making water, right? So we'd like take 2 moles of hydrogen gas and a mole of oxygen gas to produce 2 moles of water vapor. This reaction actually releases a lot of heat. And you're like, well, how much heat does it release? We can actually measure it. And when we do measure it, we report that measured value as the delta H of this reaction. And we're going to actually put a number right here where we can actually measure how many joules. I probably should have looked this up ahead of time. I don't know. I'm not going to make up a number, but we would put the number of joules that this reaction either absorbed or released. All right. And we'll do this in our next lecture. When we write equations like this, we call them thermochemical equations. And they just basically tell us how much heat is absorbed or released by a reaction. And that's it. Good job. So when you're done taking notes, take a brief look through sections 5.1 through 5.3 in your textbook. Again, don't dig too far into 5.3 unless you're like really interested in this conversation about heat transfer at constant pressure. And go ahead and do those practice problems assigned. And if you have any questions during this lecture, you can either shoot me an email or wait until I see you. All right, you guys, good job hanging in there. That felt long. See you soon.